Hello, and welcome to this FP3 exam walkthrough. This is the June 2022 paper. It takes an hour and a half, although I expect this video to be a little bit longer than that because I'm going to be explaining as I go. You have the mathematical formula booklet that you're allowed, and of course a calculator. I won't go through all of this. You've seen these plenty of times by the time you get to this exam. Jumping straight in then, number 1. Use the definitions of sinh and cosh in terms of exponentials. Okay, straight away, definitions in terms of exponentials of these two things. These are things that you need to have memorized. So you need to know that sinh of x is equal to e to the x minus e to the minus x over 2, and cosh of x is equal to e to the x plus e to the minus x over 2. And we're using these to show that this statement here is true. So it's fairly straightforward. I'm just going to put a and b for x into these expressions. So we've got cosh a, which gives us e to the a plus e to the minus a over 2, times cosh b, which is e to the b plus e to the minus b over 2, plus sinh a, e to the a minus e to the minus a over 2, times sinh b, e to the b minus e to the minus b over 2, and we need to show that this will simplify to the expression of cosh here with a plus b instead of x. And to do that we just work through the algebra. So that gives us e to the a plus b plus e to the minus a plus b plus e to the a minus b plus e to the minus a minus b, and on the bottom in the denominator 2 times 2 is 4, plus on the other one very similar, e to the a plus b, but then minus e to the minus a plus b minus e to the a minus b, and plus e to the minus a minus b, and again all over 4. Same denominators, we can add them together and we can see that this term cancels with this term and this term cancels with this term. That gives us, when we collect like terms, 2e to the a plus b plus 2e to the minus a plus b, if I write it like that, all over 4, and of course then we can cancel our 2's to give us e to the a plus b plus e to the minus a plus b all over 2, which is using the definition of cosh of a plus b as required. Part B says hence. That little word there means use the thing you've just proven to help you in the next bit. Find the value of x for which this is true. So we'll use what we've just done. We'll turn this expression for cosh here into something that looks like this left hand side up here, and then we'll simplify a few things with the log 2 and get an equation that hopefully we can solve more easily than the one that is here. So we've got cosh x plus log 2 is equal to 5 sinh x. I should make it clear for the examiner that I've started part B. And we're using what we've just proven. So this becomes cosh x, cosh log of 2, plus sinh x, sinh log of 2 is equal to 5 sinh x. And then if your calculator can do cosh log of 2 and sinh log of 2, then great. But my one that I'm using at the moment can't, so let's have e to the natural log of 2 plus e to the minus natural log of 2, which is the same as log of a half divided by 2. So this is cosh log of 2, and that gives me 2 plus a half over 2, which gives me 5 over 4. And then sinh is very similar. It'll be 2 minus a half over 2, which is 3 out of 4. So replacing those in that expression gives me 5 out of 4 cosh x plus 3 out of 4 sinh x is equal to 5 sinh x, and hopefully by this point we can see that we're just going to rearrange and get tan. If we pull that sinh onto the right hand side and multiply everything by 4, that gives us 17 sinh x and 5 cos x. Dividing through by cos and 17, 5 out of 17 is tan x. Solving this, we've got r tan of 5/17 is equal to x. And quickly pulling up the formula booklet here, we can see that we have an expression for r tan here, because the question wanted it in the form a half log k, where k is a rational number. So putting this in here, x is equal to a half log of 1 plus 5/17 over 1 minus 5/17, which gives us a half log 11 over 6, where k is equal to 11 over 6. And that is question 1 finished. Quickly reviewing it to make sure that I've done everything. Yes. Okay, on to question 2. Okay, fairly obvious that we're using integration here. Determine for part 1 the integral of this. Now that is not a straightforward integral. We've got a quadratic inside a square root. Nothing else to play around with to manipulate it. So I'm going to complete the square and see if that helps. So for part I, integral 1 over the square root of 5 plus 4x minus x squared. So if I just focus on 5 plus 4x minus x squared for a minute, that I never like a negative x squared. Let me write that like this. Now if I want to complete the square, within that bracket I should have x minus 2 all squared minus 4, and I realise many of you might not like the way that I've done that, but hopefully whichever way you do it, you end up with a 9 minus x minus 2 squared. Now that might not seem much better, but actually that now tells me exactly where we need to go next, because we have some standard integrals where we have two squareds either added or subtracted inside a square root, especially in the denominator of a fraction. If I go back to the formula booklet for a second, here we go. So integrating and just comparing which ones we want. I think it's this one here. We've got a squared, so that's our 9, minus x squared, in our case x minus 2 bracket squared, and that should give us arc sine x over a. So over here, if we integrate this, list off my dx's, we should have arc sine x, which in this case is x minus 2, over a, which is the square root of the 9, so that's a 3, and all of that is inside the arc sine. And then a plus c. And that is part I finished. Part II tells us to use the substitution x is equal to 3 sec theta. Okay, and then we're determining the value of this thing here, 18 over x squared minus 9 to the 3 over 2. And we've got limits 6 to root 3. Okay, straight away I know I'm going to need to differentiate to substitute out dx, so that dx by d theta, and differentiating sec is sec theta tan theta. If you forget that, it is in the formula booklet under the P2 section. Then we're going to need to manipulate this. So we've got x squared minus 9 inside the square root, or the 3 over 2, is 9 sec squared theta minus 9, which is 9 sec squared theta minus 1, which is the same using a trig identity as tan squared theta. So all of that tells me that this integral becomes the integral from 2 root 3 to 6 of 18 over 9 tan squared theta to the 3 over 2 dx. I haven't substituted dx or the limits yet. So let's do dx next. So we've got 6 integral 2 root 3 of 18 over 9 tan squared theta to the 3 over 2 times dx, which we know is 3 sec theta tan theta d theta. Now I still haven't done my limits yet, so this is still x equals. I will deal with them later. So looking at this, we've got 54 sec theta tan theta over applying this index gives us the square root of 9, 3, and then cubed is 27. Square root of tan squared is tan, and then cubed is tan cubed. Theta d theta. One of those, of course, cancels out with that. And the 54 over 27 cancels to give us a 2. So that just simplifies to 2 sec theta over tan squared theta d theta. And then that still looks fairly horrible to me, so I'm going to just put it all in terms of sine and cosine. So we've got the 2, and then we've got sec, which is 1 over cosine, and tan squared on the bottom, so that's sine squared theta there, and a cos squared theta there, so that tells me that one of these will cancel, which is the integral of 2 cos theta over sine theta times sine theta, and I've written it like that just to emphasize that I'm going to do a cos divided by a sine to get a cot, and then I still have a 1 divided by sine, which is a cosec. So that gives me the integral of 2 cot theta cosec theta. And that I hope you recognize as something that we can find in the formula booklet. Here it is in the same section as the derivative of sec, if you needed that earlier. So the derivative of cosec, we're told, is this. So the integral of this, we can say, is negative cosec. So all of this on this is going to become negative 2 cosec theta. But of course we still have those limits which I haven't dealt with yet. So if x is equal to 6 and x is equal to 2 root 3 are the limits we need to go all the way back to our substitution, 3 sec theta. So that's x is equal to 3 sec theta. Rearranging the first one gives us theta is equal to pi by 3, and rearranging the second one gives us theta is equal to pi by 6. So we've got pi by 3, pi by 6 here, and if I stick those on here as if I had done that earlier, then we just need to evaluate this. Minus 2 over sine pi by 3 minus 2 over sine pi by 6, which gives us minus 4 root 3 over 3 minus 4. 4 minus 4 root 3 over 3. And if I quickly go back, we want a plus b root 3, so that's good. The root 3 agrees, so a here would be 4, and b would be minus 4 over 3. And that is the end of part 2, and therefore the end of the question. On to question 3. Here we have matrices. Okay. Given that I plus j plus k is an eigenvector, Okay, I always prefer to use column vectors. So 1, 1, 1 is an eigenvector of M. Determine the corresponding eigenvalue. 1 mark. Okay, here to find the eigenvalue, we just need to apply the matrix to the eigenvector. So we have minus 2, 5, 0, 5, 1, minus 3, 0, minus 3, 6. Applied to 1, 1, 1. Yeah. Minus 2 plus 5 plus 0, minus 2 plus 5 is a 3. And if I was really confident that is all the work I need to do, the answer should be a 3, but let's just check. 5 plus 1 is 6, minus 3 is 3, and 0 minus 3 plus 6 is also 3, yes. So that is 3 lots of 1, 1, 1, therefore the eigenvalue is 3. Part B, given that 8 is an eigenvalue, determine a corresponding eigenvector. Okay, we're doing something fairly similar here, except we don't know the vector and we do know the eigenvalue. So it's going to be a very similar process with a slightly different focus. We know that this applied to the eigenvector, which we don't know, is equal to 8 lots of that same eigenvector. And then we can just apply this and equate the ij and k components. So we have minus 2x plus 5y must equal 8x. That tells me that 5y equals 10x, or y is equal to 2x. So there's a relationship between y and x. Now I also know that 5x plus y minus 3z is equal to 8y. That gives me a relationship between all three. I'll leave that for now. That's not going to be as useful as the next one because I can see a 0. So we get 0x minus 3y plus 6z is equal to 8z. So we've got 2z there and minus 3y there. So if I make x is equal to 1, then y is 2 lots of x, so that's 2. And then over here, if y is 2, that becomes a minus 6 is equal to 2z. So z is equal to minus 3. And I chose that specifically because I could see the 2 over here and the 2 over here would give me whole numbers. But if you chose values that didn't give you whole numbers, you could just multiply it by whatever your fraction was, because you don't need a very specific answer here. There are lots of possible results you could use. So we've got our eigenvector 1, 2, minus 3. Part C, determine a diagonal matrix D and an orthogonal matrix P such that this is true. Okay, what we've got so far is 2 eigenvalues, 3 and 8, and 2 eigenvectors corresponding to those eigenvalues. In order to do this, to get the diagonal matrix and the orthogonal matrix, we're going to need the third and final eigenvalue and eigenvector. And to do that, you need to remember that we need the determinant of m minus lambda I and set it equal to 0 and then solve it. So if I cheat a little bit because I'm using a tablet, this is m, and then if we do m minus lambda I, we get minus 2 minus lambda, 5, 0, 5, 1 minus lambda, minus 3, 0, minus 3, and 6 minus lambda. This is the matrix, so the determinant of this is the determinant of this. At this point you should brace yourself for a fairly long equation. We have the first element minus 2 minus lambda times by its minor, which is 1 minus lambda times 6 minus lambda minus 3 times minus 3 is 9, minus the second element, 5, times its minor, which is 5 times 6 minus lambda, minus 0, plus the third element, 0 times its minor, which we don't really care about because it's times by 0. That will be 0. And just to be really clear, all of this is the determinant of m minus lambda I, and we're setting this equal to 0. So a whole lot of algebra here. We've got lambda squared minus 7 lambda plus 6 minus 9, and all of that is still times by minus 2 minus lambda. And then here 30 minus 5 lambda, and that is still being multiplied by the 5 in front. I change this to a minus 3. Then to solve this I need to expand it all out first and then try and factorize as best I can. So we've got minus 2 lambda squared plus 14 lambda plus 6 minus lambda cubed plus 7 lambda squared plus 3 lambda, the other bracket minus 150 plus 25 lambda, still all equals 0. So that minus lambda cubed plus 5 lambda squared plus 42 lambda minus 144. Now, at this point, remember we know two of the answers already. We know that one of the values is a 3 and one is an 8. Use those to help you solve this cubic equation. So we know that lambda minus 3 is one of the factors here, and lambda minus 8 must be another one. So we've got a third bracket, and really all we need is to consider the cubic. So because we know we've got lambda times lambda already and we need a minus lambda cubed, this must be a minus lambda here. There's no other way a negative lambda cubed is going to come out of this. Similarly, to get minus 144, doing minus 3 times minus 8 and minus 144 divided by that gives us minus 6. That's the only way we can get that constant minus 144 out of this. In an exam setting, I would just leave it like that. I wouldn't check my work unless I had time at the end of the exam to come back and check it. It seems to have worked out well. In this case, minus lambda minus 6 is one of the options, which gives me the final answer for lambda is equal to minus 6. That's the third eigenvalue. We still need an eigenvector. So we're going to do the same as we did in part B, but with minus 6 instead of 8. So again, I'll just be a little bit cheeky here. Copy that down here. But instead of the 8 here, we've got a minus 6. So again, we've got minus 2x plus 5y. In this case, it's minus 6x here. 5y is equal to minus 4x. And for the same reasons as before, I'll actually skip over the middle one and I'll jump straight to the third one, where we've got minus 3y plus 6z is equal to minus 6z. 12z is equal to 3y, or 4z is equal to y. In this case, I'm going to let z equal 1, and then y must equal 4 from the second equation. And if y equals 4, over here we've got 20 is equal to minus 4x, x is equal to minus 5. So our third eigenvector is minus 5, 4, 1. At this point I can write down the diagonal matrix, because that's just using the eigenvalues, 3, 8, minus 6, and zeros everywhere else. It doesn't matter what order you put the 3, 8, and minus 6 in, so long as they go down the main diagonal, and you get the corresponding eigenvectors in the correct order in P. P then is made up of 1, 1, 1, the one we just found, minus 5, 4, 1, and the one we had for 8, what was that? 1, 2, minus 3. In this order, because of the order I've chosen the eigenvalues in D, but not these actual numbers, because we need to normalize these. So if we do 1 squared plus 1 squared plus 1 squared, we get a 3. So the first one, this is all 1 divided by root 3. To normalize that first eigenvector. The second one, 1 squared plus 4 and 9 is 14. So we've got 1 over root 14 2 over root 14 and minus 3 over root 14. And then the last one, 25 and 16, is 41, plus the 1 is 42. So minus 5 over root 42, not very nice numbers, but never mind. And 1 over root 42. And that is P. I don't need to write the equation, or use the equation even, I just needed to determine D and determine P. And I have done that, so the question is finished. Moving on to question 4. Differentiation. Immediately I start thinking to myself, let's pull up the formula booklet. Here we are, the very last one, artan, and if we differentiate that, we need this. Although I hope it's fairly obvious that that's not all we're going to need, because we've got a cos x inside of this, so we're going to be using the product rule. But let me just put down for now the derivative of artan x is equal to 1 over 1 minus x squared. So applying what we've got here, where this is y now, we've got 1 over 1 minus cos x plus a over cos x minus a squared times by the derivative of that thing in the brackets, cos x plus a over cos x minus a. I'm going to have to differentiate that using the quotient rule or in any other way. So d by dx of cos x plus a over cos x minus a. And to do this we differentiate the top, or the numerator. So we get minus sine x times by the denominator, cos x minus a, minus the derivative of the denominator, which is also minus sine x, so that becomes a plus sine x times by the numerator, cos x plus a, and all of that is divided by the denominator squared, which I'll leave in brackets for now. Now I'm expecting all of this to become k tan x, so there's a lot of simplifying that's going to happen. So if I expand this out, I'm going to expect some simplification to happen. So we've got this plus a sine x plus sine x cos x plus a sine x, all divided by cos x minus a squared. Great, so that is gone, and that gives me 2a sine x over cos x minus a all squared. So now if I put this back into dy by dx, that's just at the top of the screen there, dy by dx is equal to 1 over, and I'm going to manipulate this as well. Here, this 1, I'm going to change that into cos x minus a squared on top and bottom of the fraction so that it can add with this fraction here. So if I write cos x minus a squared over cos x minus a squared minus cos x plus a squared over cos x minus a squared, and then it's being multiplied by the derivative that we just found out simplifies to 2a sine x all over cos x minus a squared. Then what I can do is combine these two fractions here and flip the denominator of the fraction that's currently in the denominator up into the numerator. So that's all going to become cos x minus a squared divided by cos x minus a squared minus cos x plus a squared times by 2a sine x over cos x minus a squared, and that's great because all of that cancels with all of that. So now we've got 2a sine x over, let me expand these, cos squared x minus 2a cos x plus a squared, and because of the similarities here and the negative in between, this is going to work out nicely. cos squared x again, plus 2a cos x from the squared, but because of the negative that becomes minus 2a cos x minus a squared. So this one cancels with this one cancels with this one, and we end up with 2a sine x, and collecting those two terms on the bottom, minus 4a cos x. The a's cancel, and we have sine over cos, which is tan, and 1 over 2 minus a half tan x, where we wanted k tan x, so k must be minus a half. And that's all there was to question 4, just that one part. So on to question 5. Parametric equations. Okay, it says the curve is rotated through 2 pi radians about the x-axis. Show that the area of the curved surface generated is this. Okay, we've got the formula for that also in the formula booklet. So here it is. We've got 3 different versions, and they even have it labelled parametric form in the middle there. We want it about the x-axis, so yes, this is the correct one, x. Copying that out very quickly, integral y dx by dt squared plus dy by dt squared dx. We're given the limits as well, so this is going from 0 to 4. And I've actually even managed to copy it wrong, that should be a dt. Just realising as I put those limits on. So this is the formula. All we need to do for 7 marks is to work it through. As usual with this type of question, I'm not going to work with the integral just yet. I'm going to work with trying to simplify what's going to be in that square root and then put it into the integral afterwards. So we've got x is equal to 4e to the half t, and we need dx by dt. That gives us 2e to the half t, and then we need to square this. Gives us 4e to the t. Same thing with y. We need to differentiate and square it. Then we need to add them together. And that gives us e to the 2t plus 2e to the t plus 1. And if you just compare that for a moment with this expression, it's very similar except for the plus and the minus, and that gives us a little clue that we can put this into a perfect square format, or just recognizing it's a quadratic and doing it that way anyway, which is great because that means the square root of this thing is quite nice and easy. And that's what we're going to put into here, our integral. So we've got s about the x-axis is 2 pi integral from 0 to 4 of y times the square root of that thing which we've just figured out is all e to the t plus 1 dt, and of course y we need to put in as e to the t minus t. Now we work through this integration, put in the limits, and get our answer. So we've got 2 pi. To do this, I'm going to expand all of that. We've got e to the 2t minus t e to the t, which I might have to use integration by parts to do, minus t plus an e to the t dt. Yes, let me quickly just do this on the side here. T e to the t. If I call this u and this v prime, using integration by parts, that gives us t e to the t minus the integral of e to the t, which is just e to the t. So that's this term here specifically without the negative. And then if I go ahead and integrate the rest, we've got e to the 2t, so half e to the 2t, minus te to the t minus a minus, so it's plus e to the t, and then back to the integral over here, we've got minus t, integrate that, minus a half t squared, and then the last one, e to the t, is just e to the t, from 0 to 4, which gives us 2 pi half e to the 8 minus 4e to the 4 plus e to the 4 minus a half of 16, which is 8, plus another e to the 4 minus, if you put 0 in, e to the t becomes a 1, so we get a half minus 0 plus 1 minus another 0 plus another 1. Half e to the 8 minus 2e to the 4 minus 8, and then 1, 2 and a half, so minus 2 and a half, or 5 over 2, and all of that times by 2 pi. And that gives us pi lots of e to the 8 minus 4e to the 4 minus 16 minus 5, which is minus 21. And is that the form they want? Pi e to the 8, e to the 4. So e to the 8 should be a 1, yes. And the coefficients of e to the 4 and a constant, e to the 4 and a constant, yes. So a is equal to minus 4, and b is equal to minus 21. And that was all for that question. On to question number 6. Another matrix one. Show that a is non-singular for all real values of x. Okay, if a is singular, then the determinant of a is equal to 0. If a is non-singular, then it is not equal to 0. So that's what we need to show for part A. To do that, we're going to have to find the determinant of a, which we've done in a previous question. We have the first element x times by its minor, which is minus 4 minus minus 2x, minus the second element times its minor, which is minus 2 minus minus 4x, so that's a plus 4x, and then the third element with a positive times its minor, which is minus 4 minus minus 16. And if we set that equal to 0, we need to show that this has no solutions, because we don't want this equal to 0. So expanding these, we get minus 4x plus 2x squared plus 2 minus 4x. And then we've got on the end there minus 4, so that's 12 times 3, 36, equal to 0. We've got 2x squared minus 8x plus 38 equals 0. And we need to show that this does not have any solutions. So let's do b squared minus 4ac inside the square root of the quadratic formula. Gives us 64 minus 4 times 2 times 38 is minus 240, which is less than 0, therefore no real solutions. Therefore, is it A? Yes, A is non-singular, which means it has an inverse. So part B is determine in terms of x what that inverse is. So for this we just need to follow through our usual matrix inverse process. We have A is equal to x, 1, 3, 2, 4, x, minus 4, minus 2, minus 1. So this is part B. From here we need the matrix of minors. Now of course we've got 3 of them already from our work on the determinant. So So we've got minus 4 plus 2x, minus 2 plus 4x, and the third one here, 12. So those are the three we know from previous work. Now we need the others. So 2 has a minor of minus 1, minus 6, so that's plus 6, so let me just write 5. The 4 in the middle has a minor of minus x, minus 12. And the x in the right hand column has a minor of minus 2x, minus 4. Third row, we've got x minus 12, and then we've got x squared minus 6, and finally 4x minus 2. So that's the matrix of minors. Now we need to remember the pattern for the co-minors looks like this, telling you which ones to leave the same and which ones to make negative versions of themselves. So C, we leave minus 4 plus 2x, minus x plus 12, 4x minus 2, 12 and x minus 12 all stay the same. Then here we've got 2 minus 4x, here 2x minus 4, here minus 5, and here 6 minus x squared. Now we have to transpose that, CT, and that means sort of reflecting it. So again, the middle diagonal, or the main diagonal, does not change. We've got 4x minus 2, and then everything else kind of reflects, if you want to think of it like that. That becomes 12, x minus 12, 2x minus 4, 6 minus x squared, over here minus 5, and 2 minus 4x. So the inverse of A is equal to 1 divided by the determinant of A times by CT. So we've got the determinant from before. Is a strange thing, it's a quadratic. So we've got 1 over 2x squared minus 8x plus 38 times by CT minus 4 plus 2x minus 5, x minus 12, 2 minus 4x minus x plus 12, 6 minus x squared, 12, 2x minus 4, and 4x minus 2. And there we have, in terms of x, the inverse matrix of A. That is the end of question 6. Question 7. So we're given our IN is equal to this. Now that looks reasonably horrible. Show that this statement here for NIN is true. Okay, so usually for these sorts of questions, we need to do integration by parts. Not always, but I think in this case we will. Now it's a bit annoying that we've got an x squared inside the square root there. If I were to write this like this, then my instinct would be to say make this u and make this v prime, so that when we apply integration by parts, we differentiate the u term, this n decreases each time, and we can see that we need something like that because we've got an n minus 1 there, and of course we're using I n minus 2 here, so we do need that to decrease. However, if I were to do that, as I've said it, the v prime here, the integration of this is really quite horrible. In fact, we know how horrible it is because we did something not that dissimilar earlier in the paper, and we know that that came to, what was it, 9 minus x minus 2 all squared inside a square root, and it was something like arc sine. And that might sound okay, but if we've got arc sine on our next iteration, then we're trying to integrate arc sine, because we'll still want the u to be the x to the power n minus 1 term. All of that to say, this will not work very easily. It might work, if you could follow it all the way through. I don't think we've done integration of arcsine in this course though. So if you start down that route, you might suddenly realize it's not going to be very nice. It might not work at all. A sneaky trick here then is to split this x to the n into two pieces. Because if you notice here, we don't have an I n minus 1 anywhere in here. We only have an I n minus 2. And that helps, maybe, if you see that, to reinforce that this is probably the way to go. If I split this into x to the n minus 1 times x, I hope it's obvious that's x to the n when you put them together, and then we still have the 10 minus x squared to the minus a half here, and we say that this thing here is going to be u in the by parts formula, and all of this thing, including that leading x, is going to be v prime. Now the whole reason for doing that is because this is much easier to integrate, because it's all down to this x squared. That's a really awkward thing to have, because if we've got an x involved in this integration, it's not so bad, because this now is a bracket multiplied by something very close to its own derivative. So that will come from something of the form 10 minus x squared to the power half. So using our by parts formula, we get u v minus the integral of u prime v dx. So that's what I'm using. So we integrate this. U is x to the n minus 1. V is the thing that actually I'm probably going to need to do on the side here. So let's do the integral of x 10 minus x squared to the minus a half. Actually, a way that I'm really going to be thinking about this is differentiating. So if I differentiate something that I think that's going to integrate to, which is 10 minus x squared to the half, what I would get out of that would be a half times 10 minus x squared to the minus a half times by the derivative of the thing inside, which is minus 2x. The 2's would cancel, and I would get minus 10 minus x squared to the minus a half times the x on the end minus x. So make a bit of room there. What I'm saying here is that v is equal to negative 10 minus x squared to the half. Because if we differentiate this thing and get this thing, then if we integrate this thing, it gets us back to this thing. And the only difference with what I want is that negative, which I've put in here. So that's v. U prime, which we also need for the formula, is just n minus 1 times x to the n minus 2. So going back to trying to write this out, we've got u times v, x to the n minus 1, times negative 10 minus x squared in brackets to the half, minus the integral of u prime, so that's n minus 1 x to the n minus 2 times v, so again minus, so that's a plus there, 10 minus x squared to the half dx. I hope that's clear why I've done that and how I've done that to get to this point, but it still doesn't really look like what I want. The first bit does. I've got this bit here more or less ready to go. That's already here. In fact, that's exactly as it needs to be. Yes, so that's good. So that bit's ready. But I don't have this bit here yet, because I guess I've got the n minus 1 bracket there. That's fine if that stays. That's okay. But to have this I minus n minus 2 bit, I need the integral of basically what we started with, but with a minus 2 in the power there with the n. And I don't have that yet because I've got a power half here, not minus a half, which is what makes this in the denominator. So I can't change this to I n minus 2 just yet. I still have more manipulation to go. But highlighting that is telling you where I'm going to go next, because I need that minus a half in order to get this expression in the square root in the denominator of the integral. So in order to do that, what I'm going to do is just multiply it by 1 which you know I'm allowed to do. I can multiply anything by 1, it doesn't change it, but the one I'm going to multiply it by is 10 minus x squared to the half over 10 minus x squared to the half. Of course that doesn't change anything, but it does allow me to combine the two brackets in the top to make that 10 minus x squared full bracket, and then to have the half in the denominator. If you haven't done this trick before, hopefully you will be able to use it in the future, but I think if you've done lots of these, you should have seen something similar to this by now. Because the reason I'm doing all of this will become clear. Because now this bit here looks a lot like what it needs to be, and the only difference is that I've got this annoying bracket here, but that's not so annoying because I can actually just expand this out. It's just 10 minus x squared, and I know I want the 10 based on the expression in the question, and if I've got another one here with an x squared, that is going to combine, so there might be something very useful there. So let's go ahead and expand this. So we've still got this term in the front which we need, although it is a bit annoying to keep writing it out every time. And now we've got plus the integral n minus 1 x n minus 2 over 10 minus x squared to the half times 10 for the first term, and then minus n minus 1 x to the n minus 2 times x squared, all divided by 10 minus x squared to the half. Now this x squared, when I multiply that here, combines to give me x to the n, and I hope now it's really clear what I've done and what I've ended up with and why this is good. Because what we've got here is two terms that are both integrals, so I could actually split the integral there, and the second one of the two is in, and the first one of the two is 10 lots of in minus 2. I haven't quite said that right, they've both got an n minus 1 involved, so let me just write it out a little clearer. This is minus x n minus 1, 10 minus x squared to the half, and then this is 10 lots of n minus 1 times an expression that is in minus 2, and then we've got minus n minus 1 lots of an expression which is exactly what we started with, in, and all of this on the left hand side is equal to in because that's where we started way back up here. So I'm almost there. All I need to do is expand out this bracket on the end. So if I expand that out and also just rearrange a little bit here, we've got 10 n minus 1 n minus 2 minus x to the n minus 1 10 minus x squared to the half, which is the expression we wanted, but we've also got minus in plus in, expanding that final bracket out, and on the left in, so the in's actually cancel out, and we bring the in on to the left, and we've got what we need. Let me just double check. We've got 10 n minus 1 times in minus 2. Yes. Yeah. Okay. That was a lot of work. That gets us 6 marks. Now we need to apply it to find the exact value of this integral, which is I5, evaluated at 0 and 1. And we know what form it should be in, so I'll double check that matches when we finished. So this is part B. And we need I5 evaluated at 0 to 1. So if I write out what we have here, we've got 5 I5, where n equals 5. That gives us 10 times 4 times I3 minus x to the 4, 10 minus x squared to the half. And then if I use n equals 3, because I've got I3 here, so I know I'm going to need that. That gives us 3 I3 is equal to 10 times 2i1 minus x squared, 10 minus x squared to the half, and I1, we know, because we did that earlier, if n is equal to 1, then effectively it's this expression v prime, and we know the integral of that was this expression here. So we've got minus the bracket to the power half. And if you notice, if you follow the pattern, you get that expression anyway. So I5 is equal to, if I divide everything there by 5, we get 8i3, but we know what I3 is. If I divide I3 by 3, that gives us 20 over 3. Lots of I1, but we know what I1 is. I1 gives us minus 10 minus x squared to the half. So that's I1 going back into I3, which is minus x squared. But don't forget, I've divided everything there by 3 because of the 3 on the left hand side. And then 10 minus x squared to the half, which finishes off I3 in the I5 expression. And then we've got minus, and again, I've divided everything there by 5, so don't forget the over 5 there. 10 minus x squared to the half. And all of that, big brackets, needs to be evaluated from 0 to 1. But before I start with writing out, putting in the limits, let me quickly explain that we've got 10 minus x squared when x is a 1, that gives us a 9 in each of the curved brackets, and each one is to the power of half, so that expression in every case becomes a 3. So that's not so bad. And of course the x squared and the x power 4 leading terms in brackets, when they're 0, they just get rid of those terms completely. So it's not as bad as it seems. So if we go ahead and start putting this in, we've got 8, evaluating it at 1, 20 over 3, and then, as I said, that whole bit in there becomes a 3, so that's a minus 3 in there. And then we've got minus 1/3 of, and then that becomes a 3 as well. Minus 1/5 of another 3. And then when we've got the 0, we've got 8 times 20 over 3 times minus root 10, and everything else in that bit becomes 0 because of the leading x squared and x power 4 on those brackets. All of that on a calculator gives me minus 843 over 5 and plus 160 root 10 over 3. Now if we go back up, what did they want? 1 over 15 something root 10 plus something. Okay, that's good. 1 over 15 makes sense. And then a something root 10 plus a something. So the root 10 term, if we pull that out, I'm going to have to multiply that 160 by 5 to give me 800. And pulling a 15 out of the other term, 843 times 3 is 2529. So P is 800 and Q is minus 2529. Not very nice numbers, but they do match the format, so I'm going to not look too closely into that and assume that everything is okay. Given time at the end of the exam, I would of course check numbers like that. They do seem a little bit strange, but they are whole numbers, so I'm not too concerned. Okay, moving on to question 8. The plane pi has equation this. The line L1 is perpendicular to pi and passes through the point P. The line L intersects pi at the point Q. Determine the coordinates of Q. Okay, so we're going to need to know the equation of line L1, and that is using the point P plus a direction vector, but because we're told that this is perpendicular to pi, the direction vector I can use is the 3, 4, minus 1 vector here. because I know that that is perpendicular to, it's normal to the plane. So I can use that straight away out of the equation to call this an equation of L1. Now where that intersects the plane is the coordinates of Q, so I can just put this into what I've just written here, where x, y, and z will be minus 4 plus 3 lambda, minus 5 plus 4 lambda, and 3 minus lambda. So 3, 4, minus 1, and we need to dot that with minus 4 plus 3 lambda, minus 5 plus 4 lambda, 3 minus lambda, and that must equal 17. So we have minus 12 plus 9 lambda, minus 20 plus 16 lambda, minus 3 plus lambda is equal to 17. That's 26 lambda is equal to 20, 40, 52. So lambda is equal to 2. But don't stop there, because we need the coordinates of Q. So we need to put this back into the line equation and find out the actual value of the coordinates. So at lambda is equal to 2, we've got minus 4 plus 6, minus 5 plus 4 lots of 2 is 8, and 3 minus 2. I'm taking that from this here, with lambda is equal to 2. That gives me 2, 3, 1. And that is the position vector of Q, so let me write it as coordinates 2, 3, 1. That is part A finished. Given that the point R lies on pi, so that's in the plane and Q is also in the plane, determine a Cartesian equation of the plane containing PQR. So Q and R are both in the original plane, but P is not. However, I do have the coordinates of P. I now have the coordinates of Q from part A, and they're telling us the coordinates of R. So we've got the coordinates of all of them. We just need to find two vectors that are non-parallel between these three, and use that with the cross product to find an equation of the plane. I can make a little bit less work for myself here, because we already know from P to Q. We've used that already. The direction vector there is 3, 4, minus 1. So from P to Q, that is 3, 4, minus 1. And we need a second one. We've got R, let's say Q to R, minus 1, 6, 4. And Q we've just got is 2, 3, 1. Perhaps as an exam technique in passing, I shouldn't really use Q, because I might have made a mistake. And I've got P, and I know P isn't a mistake because they've given it to me. So let me just change that. We've got minus 4, minus 5, 3. Minus 4, minus 5, 3. Now hopefully it would give me the same answer, but just in case. That gives me 3, 11, 1. So I've got two non-parallel vectors in this plane. So now I'm going to cross them to find the normal to the plane. So we've got 4 minus minus 11, minus 3, minus 3, and 33 minus 12. That gives me 15, minus 6, and 21. Now that is a normal to the plane, but just to make the numbers a little bit easier, I'm going to pull out that factor of 3 and use the slightly smaller numbers instead, because that's still going in the same direction. So using that normal, we can now dot that with any one of the 3 points, and they should all give me the same answer. But again, I'm going to avoid using Q because I've calculated that myself, and it might be a mistake. Minus 4, minus 5, 3. We get minus 20 plus 10 plus 21, which gives us 11. So our equation of the plane is this. Now let's just double check. What did it say? Determine a Cartesian equation of the plane. Okay, just because of that phrasing, I'm going to rewrite it ever so slightly like this. And there we have our Cartesian equation of the plane. So that's part B finished. The line L2 passes through P and R. So P is not on our original plane, but R is. Line 3 is a reflection of line 2 in pi, the original plane. Okay, let me just try and visualize this. If we've got the plane here, P is down here, Q, we know if we need that, is on the plane. Let's say R is over here somewhere. So we're told PR. We know Q, and that's perpendicular. PQ perpendicular to the plane. Okay. Line 3 is a reflection of this in this plane, so we get, we call it P prime up here. R is obviously still the same because it's on the plane of reflection. So this is L2 and this is L3. Do we know P prime? Yes, we can know P prime because we know P to Q, we know this vector here, and because it's perpendicular, we just add on another one of those same vectors and it will take us to P prime. So we can get to P prime. Determine a vector equation for L3. Okay, so what I've just said is exactly what I'm going to need to do. Starting at P, I'm going to add the vector PQ and then add it again, and that will get me to P prime's coordinates. I'll then use P prime and R, which we already know, to get L3 in the way we did in the first part of the question. So P is -4, -5, 3. And we know the coordinates of Q, assuming we've got them correct from part A, is 2, 3, 1. Now I can't use anything else. If it's wrong, but I think it's okay. So to get from P to Q, we're going to want 2, 3, 1, minus -4, -5, 3, 6, 8, -2. Which shouldn't be a surprise because that's our 3, 4, -1 with lambda equals 2. So that takes us there. Now to get to P prime, we can go from Q and add on another one of these vectors, 6, 8, -2. So that gets me 8, 11, -1. So P prime, 8, 11, -1, is the reflection of P in the plane pi. I also still know R, and that is somewhere where it's R, -1, 6, 4. So I've got these two things and I can find the equation of L3, first by finding P prime to R for the direction vector. And then using either of these points, I'll use R so that L3 has the equation -1, 6, 4 plus lambda lots of -9, -5, 5. And that should be an equation of L3 to finish off our question, I think. Yes. On to question number 9, which I think might be the last one. The ellipse E has equation this, given L has equation this, where K is a constant, and E and L meet at two distinct points P and Q. Show that the x-coordinate of P and Q are solutions of this equation. Okay, so we're just finding where they meet. So we're using the equation for the line. We're going to put it into the equation for the ellipse. That's straightforward to begin with. So we've got y is equal to kx minus 3. So y squared is equal to k squared x squared minus 6 lots of kx plus 9. So then just substituting that into the ellipse equation, gives us x squared over 9, yep, plus y squared, which is this, over 4 is equal to 1. From here it's just algebra and multiply everything by 36, so we get 4x squared here, plus 9 lots of k squared x squared minus 6kx plus 9 is equal to 36. Then we've got 4x squared plus 9k squared x squared minus 54kx plus 81 minus 36 is 0, and that gives me a plus 45. And here factorize out 4 plus 9k squared with the x squared. And hopefully that matches 9k squared. I haven't quite written it in exactly the same format, but yes. Okay. Part B. The point M is the midpoint of PQ. Determine in simplest forms in terms of k. I don't get the feeling it's not going to be all that simple. The coordinates of M. And they're telling us from part A that the x-coordinate of P and Q are given by the solutions to this equation. Great. So we're going to need to solve this equation and then find the midpoint. That does not look like a nice equation to solve, but let's start with it. Minus b 54k plus or minus the square root of b squared, 54 squared k squared, I won't work out the numbers just yet, minus 4 times a times c. And all of that needs to be divided by 2 lots of a. Now, if like me, you look at that and think, oh dear, or you go ahead and you get a bit further in the solution here, you'll find that this is not nice, because that square root is not going to simplify to a perfect square. However, because of the question, there's a sneaky little thing that tells us we don't need to worry about that, because what we're trying to find is the midpoint of P and Q, and this is giving us the x-coordinate of P and of Q, the two solutions because of the plus minus. And when we want the midpoint, we're going to be adding those two coordinates together. So if you can see ahead here, what's going to happen is that the plus square root and the negative square root, when you add these two together, they're going to cancel out. So we don't actually need to worry about that square root at all. Nor do we need to worry about finding the y-coordinate until after we found the x-coordinate of the midpoint, because it's all happening on that same one line. So this equation that we've got, y is equal to kx minus 3, we can just put it into that once we found the midpoint coordinate. We don't need the y-coordinate of P and Q. So the midpoint, or xm, is equal to x1 plus x2 divided by 2. The first solution, 54k plus the square root, all of that in there, 2, 4 plus 9k squared, plus the second solution, which is 54k minus the square root, all that same stuff in there with the same denominator. So the plus and the minus cancel out, and we get 2 lots of 54, 108k over 2, 4 plus 9k squared, and that cancels back to 54. And I haven't done the divide by 2 yet. Let me get rid of that and put it there as a bit of a fix for now, so that xm, the x-coordinate of the midpoint, x1 plus x2 over 2, which is 54k over 2 lots of 4 plus 9k squared, and that cancels further to give the x-coordinate of the midpoint as 27k over 4 plus 9k squared. So the key point there, you didn't need to do all of the work in the square root, because when you're working out the midpoint, you're going to be adding the positive and the negative versions. They cancel out. We didn't need to worry about doing it for the y-coordinate, because now we've got the x-coordinate of the midpoint. We can go straight away using, where is it, this equation here, to find the y-coordinate of the midpoint. So we've got kx minus 3. So we've got 27k squared over 4 plus 9k squared minus 3. And it says in simplest form, so I guess I should combine this into a single fraction. So let's have 4 plus 9k squared, 4 plus 9k squared, which gives us 27k squared minus 12 minus 27k squared. How nice. All of that is over 4 plus 9k squared. That was definitely worth doing. That is much simpler, just to have minus 12 over 4 plus 9k squared. So the midpoint has coordinates 27k over 4 plus 9k squared minus 12 over 4 plus 9k squared. And that is part B finished. Part C, hence show that as k varies, m lies on the curve with equation this, where p and q are constants to be determined. Okay, here we do our usual trick. We're going to take those coordinates of the midpoint and let x, capital X, equal 27k over 4 plus 9k squared, and capital Y equal minus 12 over 4 plus 9k squared. And then, because of the equation we need to show, I'm going to square them both, and then I'll just put it in here and see what we get. Let's see if we can find p and q. So squaring x, we get 27 squared, 729k over 4 plus 9k squared squared, I'll leave that. And the y squared, 144 over 4 plus 9k squared squared. And then we are looking for x squared plus py squared equals qy. X squared plus py squared is equal to qy. So if I put all of these in, then we'll have nothing but k's and numbers, and we should be able to hopefully equate and find out p and q. So we've got 729k over 4 plus 9k squared squared plus p lots of 144, let me write that, 144p over 4 plus 9k squared squared is equal to q lots of y, so minus 12q over 4 plus 9k squared. Getting rid of all of those fractions, 729k plus 144p is equal to minus 12q times 4 plus 9k squared. Expanding that, we get minus 48q minus 108q k squared, 144p, 729k over here. Well, now that does not equate, which makes me think I've made a mistake. K squared. There it is. Well done if you saw that earlier. K squared, k squared, k squared, k squared. So now, yes, okay, so now we've got k squareds, which need to match, gives us 729 must equal minus 108q. So q must equal minus 27 over 4. And then the constants, we've got 144 p must equal minus 48q, but we know what q is now. So we've got 144p, and that gives us 3, 2, 4. Dividing through, that tells us that p is equal to 9 over 4. So q is equal to minus 27 over 4. P is 9/4, and that is the end of part C, which I didn't label. That should have started here. And I think that's the end of the paper. Yes, so I hope that's been helpful walking through this June 2022 FP3 paper.